Hey everyone, in this video I'm going to explain some parts of a parabola and some basic dynamics of a parabola, what makes it and how it changes as a function changes. So let's go ahead and jump right in. First, I want to give a quick shout out to Desmos.com for providing free online amazing calculators that can do more than just graph regular stuff. As you can see in the background, lots of people put up their artwork, so if you're interested, please stop by Desmos.com, create a work of art, and share it in the global community. Alright, let's go ahead and jump right in. So I have a general function, y equals ax squared plus bx plus c over here at the top left corner, and it creates this parabola that you can see on the right side. Now there are some features of this that I'm going to explain and some features that I won't get too much into in this video, but let's go ahead and begin. So I'm going to start by activating the video here, and you can see that that as the a value changes, the parabola changes as well. It opens up or it gets skinny, and then at one point it completely flips upside down. Now I'll freeze it here for a moment in just a second right there. Oops, I didn't freeze it, did I? There. I still didn't freeze it. Okay, so it's at 1.6. So our a value is 1.6, which is something greater than 1. What happens is when you have a value that gets increasingly bigger than 1, the parabola closes up. Contrary to what we might think, this is a bit counterintuitive. We tend to think, oh, the bigger the number, the larger something is because of that, right? Like a larger graph, a longer graph, or a taller graph. Well, in a way, this is kind of like that, but it's also different. Taller in the sense that you get skinnier and you shoot up a lot faster than if your a value is smaller. You can see over here, if I return it to, well, where did it go? There. If I return it to about 0.7 or about 1, then we get something that is a lot more open, right? If I were to move this and make it negative, whoops, not the graph, get back here. So let's put this back where it was, and let's move the a value. If I move the a value and I make it something negative, then what happened is the parabola flips upside down. That's because we want to think of negatives as being the inverse or the opposite of positive. So if we were to have a mirror, then the negatives would be one side of the mirror and the positives would be the other side. So the negative would be like the reflection of the positive and vice versa. If we change the b values, I'll play the b over here. There we go. You can see that it moves the parabola but in a different way as well. So it seems to slide it left and right, left and right, left and right. Okay, and if I play the C, then it does shift it up and down. So it moves this down and up. That's because the C value affects what's known as a y-intercept. And the C value is simply your constant, which is the value at the very end of your function. It's the one that has no variable x attached to it. Okay, so it controls where that y-intercept is, and it gives the illusion that the whole thing is being moved up or being moved down. Okay, so I'll pause it there. Now, there are some features of a parabola that are important to know now that we kind of understand why some are upside down and why some are right side up. Some parts of a parabola include the y-intercept, as I already explained, so we're going to start there. To get the y-intercept of a parabola is pretty simple if you know the function that belongs to it. In this function over here, we have everything we see. First of all, I do want to note that the reason this parabola is upside down is because of that little one right there at the very beginning. That is your leading coefficient because your highest power is a 2. And because of that, this a value being a negative number causes this parabola to flip upside down. Okay, getting back to the y-intercept. We have at the very end a +3, and if you look closely we can see, hey, that +3 is part of the parabola, and there it is. It's that green point sitting on the y-axis. So like with any point, there's always an x and a y combination of values. So the y-intercept is actually not just 3, but 0, 3. Okay, 0, 3. Alright, The next part, to identify, in my opinion, would be the axis of symmetry, or the AOS. The axis of symmetry is a line which divides the parabola into two equal parts. So this is known as the AOS. If you can imagine a line that goes right down the middle of this parabola, and it goes right down the center, it cuts it in half so that we have two equal parts. That line is the AOS, or the axis of symmetry. Now, one thing to note about this is where it cuts through the x-axis, which is right there. It happens at this location you see here. It happens exactly at -1. So when you write the axis of symmetry as an equation, you have to use the value on the x-axis that it actually cuts through. And the equation will start with x is equal to, and it will finish with the number that it cuts through on the x-axis, which in this case is -1. And that's it. That's the equation for the AOS, or the axis of symmetry. Now, what's also good about this is that it gives us something else for free. It gives us information about the vertex. The vertex is going to be either the highest point, as you can see over here, or in some cases it will be the lowest point, as we will see in the next example, which is right there. So in this particular case, it's the highest point because the graph goes up and then it passes this switch point, which is right here, and then it begins to go down on the other side. If we look at this going from left to right. So the vertex happens to have the same x value as the axis of symmetry, which is -1. See, it's the same one. So knowing the AOS helps us to also know part of the vertex because they have the same value. So what about the y value? Well, in this picture we can see easily that it's at +4. So labeling the y-axis here is actually very simple. The vertex is at -1, +4. What if you didn't have a picture to look at? Well, if you could get the AOS and know that your x value is -1, then all you'd have to do is plug that -1 into this spot and into this spot and break everything down according to the order of operations, and whatever you get in the end would, hopefully, if your math is right, be a +4, and that would be your y value. Okay? But that's in another video. Anyway, let's go on. So we have the y-intercept, we have the axis of symmetry, we have the vertex, and I'm going to relabel this because I do believe that the vertex is one of the most important points, if not the most important point, in a parabola. Next, we're going to look at the x-intercepts. The x-intercepts are the places, or the place, where the parabola, or any graph for that matter, cuts through the x-axis. The x-axis is down here, so if you have a, whoop, that's not the x-axis, is it? It's actually right there. So any graph that cuts right through that would be considered to have an x-intercept. Some graphs will have more than others, some will have none, and it depends on the function you have and how it designs the graph. So in this particular case, we can see that our graph has two x-intercepts, one right there and one right there. And because they each are points, they will each be represented by an ordered pair. And I believe I just erased my AOS line, so I'm going to have to redraw this here. Look at that, I think I did a better job than I did the first time. Alright, so let's get back to the x-intercepts. One x-intercept is right there, and I would have to write that as an ordered pair, so this would be -3, 0. And then the other one is right there, and this would be 1, 0. So I'll make them a list over here to the side, -3, 0, and 1, 0. Just a little caution, sometimes I hear students say -3 and 1, and they don't include the y component of those numbers. The reason why that's not a great idea to do is because you have to remember that a coordinate plane has two number lines crossing each other. And if we only say -3, then it's not clear whether we refer to this -3 or that -3. And we want to be very clear about things. So that's why ordered pairs are necessary whenever referring to locations. All right, so we have our x-intercepts and everything else. So what else is there? Well, the last thing is the domain and the range. Whoops. The domain represents all the x values that exist on a graph, whether it continues forever or it's terminal, meaning that it comes to a stop at some point. So it represents all the values along the x-axis. As the graph changes, the x values also change, because as we know, graphs are made up of millions of points that are connected together. And when we zoom out, it forms what looks like a solid graph design. So we have to represent the domain as all the x values that exist on the graph from its beginning to its end, if we know what those things are. In this particular case, we have to notice that we have arrows on our parabola. And what this means is that the parabola continues on forever, going straight down as the arrows are pointing. But something else is also true. Whoops. Switch actually to this over here. Oh, where did it go? Okay, let's put this back because I do want to show you something here. I'm going to make this positive again. And then I want you to see something here. I'll put that aside. So here's a parabola, right? What the function is irrelevant in this case because it doesn't matter, because I'm making a different point here. So if you were to follow this graph, which is bouncing around everywhere, if you were to follow the graph and go up, what you might notice is, first of all, the numbers get really big. Secondly, this graph seems to be opening and opening wider and wider and wider. And there doesn't seem to be any indication that it's going to stop anytime soon. Now I'm nearing 1,000, and I've now passed 1,000, and it just keeps getting wider. I'm not zooming in, I'm simply scrolling up and up and up. And what the reason is for this is because this graph, number one, is infinite. It keeps going up forever, and that's what the arrows represent. Now, in order to see more, I'd have to zoom out, and then we can see more of the graph, but I can keep scrolling, and eventually this thing is going to keep getting wider and wider and wider, and eventually the left and right red that you see is going to disappear off the screen. Okay, I'll zoom out, and you can see this is going to look very skinny because I'm zoomed out several times. In fact, I'm zoomed out, or I was 1,000 times. Let's zoom back in and get reclaim the nice friendly shape that we had. Okay, this is where it started. And so in order to represent all the possible x values that we could have, because this does go on forever, we do need to say that the domain stretches from negative infinity all the way to positive infinity, okay? And domain represents your x values, since we're talking about width, and that is your x. And so because we don't have, we cannot put a point on infinity, since it runs on forever, and it's very elusive, we simply put less than and less than to indicate that there is no closure to that, okay? And this is one way to represent domain. Now, there is a different notation. This notation I showed you here is called inequality notation. There is another notation called set notation. So I do want to quickly introduce that to you. So first, this is inequality notation, okay? It's good to know what to call things because everything has a name. Okay, the other way to show this though is what's called set notation. And that works this way. So anything that is open-ended, that you cannot put a point on, or it's broken at that place, you put a parentheses. So because infinity is not something you can put a point on, we're going to have parentheses, and then you put negative infinity, comma, and then you put positive infinity to represent the right side of 0, right? So the positive direction, it gets wider and it goes to infinity. The negative direction, it goes to negative infinity. You put parentheses to show that these are not closed areas. It runs on forever. Okay, and this is called set notation. The third way to show domain is by using a special symbol that represents an idea of everything. So because the domain of parabolas goes on forever, it covers all possible numbers. That means positives and negatives, and it covers decimals on the positive side and the negative side. It covers fractions. It covers all these different types of numbers that we know and understand in our real world. So it's possible to say for the domain that it simply covers all real numbers. So all real numbers. The cool thing about math is that it's full of different symbols that represent whole ideas. So we can take this idea of all real numbers, right? All the positives and negatives, the number 0, decimals, and fractions. We can take all of this and we can simply summarize this as the following. We can say, we can put these two parallel lines and then make what looks like a double R, right? That's a pretty cool looking symbol in my opinion, but that means all real numbers. So when you put that R, you are saying automatically everything that we already explained over here and everything that we already explained over here. It's the same thing all rolled into one nice package, which is all real numbers. However you want to represent it really depends on what your teacher will allow you to write and what you understand and feel most comfortable. But I do want you to understand that all three methods are acceptable and they are part of the way that we explain domain, okay? At least for this particular case of parabolas. All right, so that covers domain. So what else? Well, we have one final thing, and that's range. Okay, now for most parabolas, I do have to say before we get into range, when we have these arrows at the bottom or at the top, like we will in this example here, oops, like we have arrows over there, right? And that means that this parabola will go up forever. If we don't have arrows and instead what we have are solid points. Solid points. What that means is that our parabola graph comes to an end at some point, and it comes to an end and we have to represent that here. So we're not talking about infinity anymore because we stop the graph. Most of the time, however, at least for these purposes, you will see arrows because mathematically for these examples, it's simple to work with. So let's get back to the current example that we were on and let's talk about range. Range is about the height or how tall a graph is and from where to where it goes height-wise. So imagine you were measuring your height. You would measure from either your head to your feet or from your feet to your head. And you would do the same thing for parabolas. So if you look at this one over here, this parabola goes down forever, right? So it wouldn't make sense to try to measure the height of the parabola from the bottom since there is no end to the bottom. So what you want to do instead is measure from the top and then explain what happens as you go down. So because the vertex is located at, what's that, -1 and 4, and the range has to do with y numbers, y values. What we're going to look at is how the y values change once you go below that level. Okay, so this graph goes no higher than level 4, which means that the highest y value that you'll ever have on this entire graph is +4. So a quick way to show this would be to write it this way. You say all the y's for this graph are going to be less or equal to 4. Okay? All the y values are going to be less than or equal to 4. And it makes total sense if you think about it because well, like I said again, the highest value for the y on this graph is a +4. There is nothing higher than that. There's another way to show that using inequality notation. Even though this is an inequality, if you want to show it in its full form, you can show it like this. You could write that the graph goes from -infinity, right? So from here, it rises, and I should put that arrow somewhere else actually. So from -infinity, which is deep down below. It goes from negative infinity all the way up. It rises all the way up. And then it hits this maximum height over there of positive 4. So from negative infinity all the way to positive 4, the y's are between those two, right? And because infinity, once again, is something that we cannot put a point on, you cannot put your finger on and say, aha, that's where infinity stops. You put a less than without the equal component. But at 4, that's where the graph hits its maximum height. So we could actually put a point there. So we put a bar to show we are closed at that place, okay? And there you go, everybody. That's the domain and the range for a parabola. And with that, I want to jump quickly into our final example, which is over here. And all I'm going to do for this one is identify the domain and range, and that's it, okay? So for the domain, again, we're going to have the domain. I'll give you the different ways to write this. If you do it inequality notation, inequality style, it would be, where's my ink? There we go. Negative infinity to positive infinity. And domain is about your x's, so you put that in the middle. Infinity is something elusive. You cannot put your finger on it, you can't put a point on it, so you leave these open. That's inequality notation. Set notation would be parentheses, negative infinity, and positive infinity, okay? It shows the same thing as above with the inequalities, but using a different notation called set notation. And then if you wanted to use, to write it with just a symbol, the symbol would be simply all real numbers, okay? And again, that means all the numbers. 0, negatives, positives, decimals, everything. Okay, that's domain. For the, oops, shouldn't do that. So for the range is a little different. So let's go ahead and do inequality notation for this one. And I'll also show you set notation, by the way, which I should have done in the last example. But here we go, inequality notation for the range. So the range in this example starts from the lowest point. The lowest point on this is negative 4. It doesn't dip down anywhere below that, but it goes up forever, right? To infinity and beyond. I hope I can say that without getting a call from Disney saying that I cannot say that. But to infinity, we'll leave it there. So what I need to do is show from the lowest number, which is negative 4. It goes from negative 4, whoops, from negative 4 all the way up to positive infinity. Okay, so I put from negative 4, so from and to. From negative 4 to positive infinity. The range is about y, so you put that in the middle. At negative 4, we have a closed point. As you can see right here, it's closed up. So we are allowed to put less or equal to. But because infinity, we cannot do that, since it just keeps going, you put less without the equal part. Okay, that's inequality notation. Let's do set notation. Wait, before that, one more inequality that you could write, and this is an alternate answer, okay? Is you could write simply y's are greater or equal to negative 4. All right, if you want to write the absolute shortest way, that's the way to do it. All the y values on this graph are from negative 4, and then they get bigger. They increase in value, in size. Okay, set notation. Set notation would be based on this inequality notation here. And so at negative 4, because we have a closed point, instead of parentheses, I'm going to use a bracket. Brackets mean that you have a closed point at that place. You can actually put your finger on it and say, that's where it is. So bracket, negative 4, all the way to positive infinity. And because infinity is not something you can put your finger on, you leave it open with the parentheses, and that's domain and range, everybody. So I hope this video helped you to better understand the concept of domain and range for parabolas, also identifying parts of a parabola, and the concept of how parabolas change according to the different components that make up the function for that parabola. It's a very interesting graph, a very interesting function, and a very interesting topic within algebra studies. So if you have any questions, please stop by, leave a question or a comment, and thank you for taking time to watch. See you next time.